Hi class, today we are going to discuss one of the easiest chapters in engineering statistics, which is correlation and simple linear regression. First of all, this chapter is a bit different from the other chapters because what we're going to study would be the relationships between two variables. Okay, let's look at the objectives of the chapter. First, you'd be able to understand and interpret the terms dependent and independent variables. Secondly, you'll be able to plot a scatter diagram which describes the relationship between the dependent and independent variables. Thirdly, you'd be able to recognize the types of relationships between the dependent and independent variables from the scatter plot. And next, you'd be able to calculate and interpret the correlation coefficient. Then you'd be able to model the regression line using the least squares method. From the simple linear regression model, you'd then be able to compute the expected value of the dependent variable given the value of the independent variable. And finally, you'd be able to make inferences about the slope. As I've mentioned before, in this chapter, we would be discussing the relationship between two variables by first looking at the value of the correlation coefficient, or R, and then by creating the simple linear regression model, which goes by y hat equals to a plus bx. Now, the correlation coefficient would simply be a single value that describes the strength of relationship between the two variables, which is the y, or the dependent variable, and x, the independent variable. The simple linear regression model, which looks like a straight line. Previously, we've learned about y equals to mx plus c, and this is just a variant of the straight line. The simple linear regression model describes the relationship between y and x using a mathematical formula. Let's discuss y, or the dependent variable, and x, or the independent variable. So the independent variable, or x, is exactly what it sounds like. X stands alone and is not changed by any other variables, including the dependent variable. And y, or the dependent variable, is also exactly what it sounds like. The dependent variable depends on the independent variable. So the dependent variable represents the output or outcome by altering x, the input, or the independent variable. So the easiest way to remember is that the dependent variable always depends on the independent variable. Let's discuss a few examples to strengthen our understanding on x and y. In this example, a lecturer might want to look at the relationship between the number of hours her students spend studying and the final examination marks. So in this case, the final examination marks depends on the number of hours her students spend studying. That means, in this case, the final exam marks would be the dependent variable. So the number of hours, or the time spent studying, would be the independent variable. Let's look at more examples. Here you have the price and the age of a car. So the price of a car always depends on the age of the car. In the next example, we have the number of computer jobs and the CPU time required. What do you think would be the x and y variables? So the time depends on the number of computer jobs per day. This would be y, and x would be the number of computer jobs per day. This would be the x. Next, we have wage and working experience. So the wage or the salary always depends on the working experience. More examples. We have distance traveled and time. So the time taken always depends on the distance traveled. Here we have savings and income. So usually how much savings we have always depends on our income. Next, we have revision hours and the grading that we receive. And usually, the grading that we receive from our lecture depends on the number of hours we put into revising. So the grading would be Y, depends on revision hours X. And next, we have balloon pressure and room temperature. Of course, the pressure depends on the temperature. Okay, let's move on to correlation, the concept of correlation. So the correlation coefficient is denoted using rho for population data or R for sample data. And this is what we normally have in our exercises or exam, the sample data. So we normally use R for correlation coefficient. And what is correlation coefficient? It's simply a value that tells us how strong is the linear relationship between the variables x and y. So a correlation coefficient is a value, and the value of the correlation coefficient ranges from -1 to 1. Now, when we have -1 as the value of our correlation coefficient, this tells us that it is a perfect negative correlation. And if we have +1 as the value of the correlation coefficient, it tells us that it is a perfect positive correlation. I will describe the relationship further using a scatter plot where you could see what perfect negative correlation and perfect positive correlation means. The closer the value is to either 1 or -1, the stronger the linear relationship is between x and y. That means as the value goes towards 0, it indicates weak linear correlation or weak linear relationship. And so because we are dealing with positive and negative values, when we have a negative value, it indicates inverse relationship between x and y. And when we have a positive correlation coefficient, it indicates a direct or a positive relationship between x and y. Now, a value could only tell us about the strength of the relationship. To illustrate further, we need a scatter diagram. Now, let's discuss about scatter diagrams. So, scatter diagrams is a plot or a graph of the paired observations between x and y, which is very helpful in detecting the relationship between the dependent and independent variable, or the x and y. By constructing the scatter diagrams, we could immediately determine whether the relationship between x and y is linear or non-linear. So let's plot a scatter diagram. In this case, we have food expenses and income. And usually our food expenses depends on how much income we have. So we have, and because this is a sample data, we no more use the capital Y and X. We use the lowercase y and x. So the x-axis would be the x values, and the y-axis would contain the y values. So y starts from 50 and ends at 280. 100. I would scale it like this. The maximum value would be 300 and 50, 150, 250, and we have the incomes ranging from 500 to 2,500. So we have 500, 1,000, 1,500, 2,000, and 2,500. To plot a scatter diagram, we simply plot the values of x and y. So when x is 500, y would be 50. So I would plot this value using either a dot or a cross. Next, when x is 1,000, y would be 100, x 1,000, y 100. Next, x is 2,200 and y is 250. So 2,200 and 250. And next, x is 2,500 and y is 280, somewhere here. And here you go. This is your scatter plot. So a scatter plot does not contain any line. That means you do not have to connect the crosses or the dots in a scatter plot. Okay, we will be constructing the line using the linear regression model, which we will learn in a short while. Okay, I hope this is clear for you. For a scatter plot, you simply plot the values of x and y. You do not connect the dot. Connecting the dot comes later when we learn about linear regression. Okay, let's look at this scatter plot between x and y. You could see that this is a perfect relationship, where as the value of x increase, the value of y also increase. So when all of the points in the scatter diagram lie in a straight line with an upward slope, this is called a perfect positive linear correlation. And our correlation coefficient, or our R, would be equals to 1. What we could see here is as the values of x increase, the values of y decrease. And here we have the correlation coefficient as -1. It is a perfect negative linear correlation because all of the points lie on a straight line with a downward slope. And this is what we usually encounter in a scatter diagram. We have some values of x and y which looks scattered. However, as the values of x increase, the values of y would also increase, and the plots are scattered. It does not lie on a straight line. So in this case, the correlation coefficient would be greater than 0, and we simply interpret that as positive linear correlation. Here we have another scatter plot where the plots do not lie on a straight line. It is a bit scattered, but we could see that as the values of x increase, the values of y decrease, and so the R, or the linear correlation, would usually be negative, and we interpret the value as negative linear correlation. If the plot looks something like this, in which we can't detect the relationship between x and y, then the correlation coefficient tends to be very close to 0, and we interpret that as little or no linear correlation, which means no linear relationship exists between x and y. And here we have a quadratic relationship between x and y. Thus, our correlation coefficient, R, would be very close to 0, and we interpret that as very little or no linear relationship between x and y. This is how we interpret the values of R. When R is positive or negative 1, then we have a perfect. So it's either positive or negative linear correlation. So when R is between 0.7 and less than 1, or when R is greater than negative 1, less or equals to negative 0.7, then this describes a strong positive or negative linear correlation. When the values of R are from 0.3 to 0.7, or negative 0.7 to negative 0.3, then this has medium strength. Usually we interpret this as simply positive or negative linear correlation. And when R is from 0 to 0.3 or negative 0.3 to 0, we have weak positive or negative linear correlation. And when R is equals to 0, that means there's no linear correlation. So when R is equals to 0, there is no linear correlation. Now we have arrived to the formulas on how to calculate the linear correlation coefficient. And again, here we have the sum of squares similar to ANOVA. Now these values are easily calculated using our calculator, and I'll show you in a short while. So we have the sum of squares of xx, which is simply like your variance formula, only that we do not divide by n minus 1, and the sum of squares of yy, which is similar to sum of squares of xx, only that we use the variable y, and then we have the sum of squares of xy, where instead of x squared and y squared, we have xy, and here we have the sum of x multiplied by the sum of y. And R, or the linear correlation coefficient, is the sum of squares of xy divided by square root of sum of squares of xx multiplied by sum of squares of yy. Now, in order to calculate the values of summation of x squared, summation of x, summation of y squared, summation of y, summation of xy, we could use our calculator. If we have the FX570MS, you would press mode twice and then select regression and select lin for linear regression, and then you would enter your data, x, y, press M plus up to the end of the data set, and then you press shift 1 or shift 2 to find the summation values of x and y, or to find the value of r. Now, if you have the FX570ES, please Google how to use your calculator to find the linear correlation coefficient. Otherwise, you can check my uLearn page for the video. Class, let's discuss this past year question. The question asks us to construct an appropriate table to determine the linear correlation coefficient. That means we need to calculate the value of R for the data in table Q1. Next, give a brief explanation of the linear correlation coefficient value. So first, we need to construct a table, and then we calculate the value of R, and then we explain what R means. This question is quite easy because they have already determined that X would be the density of steel. So this would be the X value, and Y is the scale reading for a steel machine calibration. So this is Y. Let's construct an appropriate table then to determine R. What values do we need to determine R? Let's look at the formula provided here, and this formula will also be provided in your final exam. Okay, so the values that we need to calculate would be summation of x, summation of y, summation of x squared, summation of y squared, summation of xy. We have x, which is 10, 10, and then we need the values of x squared, y squared, and xy. Because the question asks for the table, and usually even if the question doesn't ask for you to construct the table, you would need to insert the values of x squared, y squared, and xy because there would be marks for this class. But what is more important to calculate R would be the summation of x, summation of y, summation of x squared, y squared, and xy. So in order to get these values, we would be using your calculator. Now, if you have the FX570MS, you would do this with me. So first, go to mode, press mode twice, choose number 2, which is REG or regression, and then choose number 1, which is LIN or linear. Then you would insert the value of x, press comma, and then insert the value of y. So we have 10, and then press comma. Comma is on top of the delete button, DEL button, the red one. Please keep in mind that you insert the value of x, y and not y, x. So we have 10, 1.2, then press M plus or memory plus, and you would get n equals to 1. So you would do this until the end of your data. So you would press again 10, 1.5 m plus, 10, 2 m plus up to 50, 8.5 m plus. Okay, once you are done, go to shift 1 and you could choose the value 2 to get the summation of x. So the summation of x is 220. To get the summation of y, go to shift 1 again and then go towards your right some more and then press 2 for summation of y. So summation of y is 38. Then you could get the summation of x squared, 8,200, summation of y squared, 251.08, and summation of xy, which is 1,433. It is important that you try this out yourself and check your answers with my answer. For those who have the other calculator, the FX570ES, go to my Ulen site and there would be a video for your calculator. Otherwise, you could simply Google. Okay, so we have these values and now we are supposed to calculate the values of the sum of squares of xy, xx and yy. Now, in your exam, in order to save time, I would straight away calculate the sum of squares of xy, xx, yy, calculate your r. And finally, when I finish all of the exam questions and I still have the time, then only would I insert the values of x squared, y squared and xy. Because to write out the values, it takes a lot of time. And it's okay if you miss a few marks not writing out the value, then missing out a few questions because you didn't have time to finish up your questions. So, but right now I will just insert these values because we have the time. Okay, this would be 100, 10 square is 100, 100, 20 square is 400, so okay, then xy would be summation of xy, which is 1,433, minus sum of x, which is 220, multiplied by sum of y, which is 38, divided by n. You could also get the value of n from your calculator. And n is equals to 8. So this would give us 388. xx would be summation of x squared, which is 8,200, minus summation of x, 220 square over 8, and this gives us 2,150. SSYY is summation of y square, 251.08, minus summation of y, 38 square over 8. This gives us 70.58. Okay, let me use this space here to calculate the linear correlation coefficient, or R, is equals to SSXY divided by square root of SSXX multiplied by SSYY. And this gives us 0.9960. Okay. And next, we are supposed to give a brief explanation regarding the linear correlation coefficient value. Now, 0.9960 is very close to 1. So it lies between 0.7 and 1, which we have discussed previously, right here. So 0.99 is between 0.7 and 1. That means the way we interpret would be strong positive linear correlation. Strong positive linear correlation. That's it. Okay class, so this is a short video that explains the concept of independent and dependent variable, helps you create a scatter plot, helps you understand the concepts of correlation coefficient, and then explain the process of calculating the linear correlation coefficient and how to interpret the value that you have calculated. So I hope that I managed to capture your interest and you are excited to learn more about correlation and linear regression. So I'll see you in the next video.